You know, we've mapped the human genome, we've split the atom, but arguably the greatest frontier of all is still right here, behind our eyes, the human brain. Today, we're diving into the incredible quest to not just understand it, but to actually build a version of it.
So, can we do it? Can we really build a working model of the human brain? I mean, it sounds like something straight out of science fiction, but this is quickly becoming a very real, very concrete scientific challenge. Before we get into the how, we really need to get a handle on the sheer scale of what we're even trying to do here.
Okay, so get this. Your brain, right now, has about 86 billion neurons, and those are connected by hundreds of trillions of synapses. The complexity is it's on a scale that's so vast, simulating it has pretty much always been seen as computationally impossible. Until now, that is.
Because that idea of impossibility, it's starting to crack. A team of researchers in Germany just made a huge breakthrough, and they did it using Europe's brand new Jupyter Supercomputer to build a model on a scale that's never, ever been seen before. So the key to all of this is a totally new class of machine, the exascale supercomputer. What are we talking about? We're talking about a computer that can perform an exaflop. That's a 1 with 18 zeros after it, calculations every single second. This isn't just a little bit faster, it's a fundamental leap in computing power.
But what's really fascinating is how they're building this thing. It's not the kind of AI you find in most language models, no. They're using something called spiking neural networks, which are designed from the ground up to mimic biology. Instead of constantly number crunching, these neurons only fire when they have something important to say, sending these little discrete spikes of info. It's kind of like being in a room where people only speak when they have something useful to add. It's just way, way more efficient.
And by using this super efficient method, the researchers pulled off something stunning. A model with 20 billion neurons. Now, to put that in perspective, that's roughly the scale of the human cerebral cortex. You know, the part of our brain that handles the heavy lifting, like reasoning and language. This is a huge milestone.
Okay, so is this just about hitting a bigger number to get a headline? Absolutely not. See, what's so exciting is that with neural networks, scale isn't just about quantity. It can lead to a change in quality. When you get big enough, entirely new properties can just emerge from the complexity.
And this chart really puts that leap into perspective. For decades, we've successfully modeled tiny nervous systems, like the 302 neurons of a worm. Going from that to 20 billion? Well, it's not just a step up the ladder. It's like taking a rocket to a whole different galaxy of complexity.
As the lead researcher, Marcus Diesman, explains it, these emergent properties are the real prize. Think about it like this. A single molecule of H2O isn't wet, right? Wetness is a property that emerges when you get billions of them together. The hope here is that at 20 billion neurons, you might start to see complex behaviors emerge that you'd never ever find in a smaller model.
Now, the promise here is incredible, but it's really important we stay grounded. This is a monumental step for sure, but it's still a simulation. It's not a brain in a box. So let's kind of balance the hype and look at both the amazing scientific payoffs and the very real, very practical problems.
I mean, the potential payoffs are just staggering. Just imagine being able to model how memories are formed in real time, or safely testing virtual treatments for disorders like epilepsy. This kind of tech could completely revolutionize neuroscience and medicine as we know it.
But, and it's a big but, here's that crucial reality check from neuroscientist Thomas Nowotny. He says, size isn't everything. This is a digital model, and it's using simplified neurons. It doesn't have a body, it doesn't have senses, and it's missing that whole complex chemical soup of hormones that are constantly affecting our brains. Just being big doesn't mean it's accurate.
And then you have what might be the biggest hurdle of all, efficiency. Your brain, this unbelievably powerful machine, runs on just 20 watts of power. 20. It is an absolute masterpiece of biological engineering.
While the Jupyter supercomputer, it chugs down megawatts of power, enough to power a small town. And this isn't just a fun little fact. It might be telling us that our current approach of just using brute force is the wrong path. The real revolution won't just be mimicking biology's scale, but one day, finally, matching its incredible elegance.
So where does that leave us? Well, this achievement isn't an endpoint. It's a new beginning. It's a really critical signpost on a long, long scientific journey. And this breakthrough didn't just appear out of thin air. You have to remember, back in 2013, simulating just 1% of the brain for a single second was a massive achievement. Now, after more than a decade of hard work from groups like the Human Brain Project, we've finally reached the scale of the entire cortex. This really is the payoff for years of global effort. And that leaves us on the edge of some really profound questions. We're not there yet, not even close. But as these simulations get more and more realistic, we have to start asking ourselves, if a model begins to show properties that we associate with consciousness, what are our ethical obligations to it? That's a question this incredible science is forcing us to think about right now.